Hello and welcome to the first video in this week's set of videos where we're going to be discussing lots of very interesting topics. So this week is all about design principles, refactoring our code, and really getting into like the nitty-gritty of designing code to be beautiful. So our very first topic on in this sort of suite of topics is going to be on this idea of cohesion, coupling, and how we can actually separate these things apart and separation of our concerns in our code. So let's jump right in. So I really like this quote, and it felt exactly right. Code is read more than it is written, right? So we have to remember that design quality isn't optional, right? We can't be writing garbage code. We can't have bad variable names. We can't leave our comments to the end, because at the end of the day, the reality is our code is read more than it's written. We write it once and now it lives there forever, right? In the real world, your code now lives there. People will come along and read it for like years to come. Written once, read a ton. So there's a reason why we have to take a step back, slow ourselves down, and do a really good job of designing maintainable and beautiful code. So we really need to ensure that we have that clean design. It's going to allow us to reduce bugs, which is obviously great for us, but that honestly will just speed up our development overall. Bugs take up something like 75% more time than creating the bug took. So really we are talking about the fact that it's like slow and steady wins the race, kind of like a lame turtle hair, idiom, but taking shortcuts just never ends well in the long term. There's a reason why these processes exist. So I haven't talked about this. Maybe I have. Now, I've mentioned this before, but it's worth mentioning again, right? That design quality isn't optional. I have a friend who used to work at Google, and they put up their first code review for their team to read it. And the code review went through 23 rounds of comments, right? So this means that they received comments, went to fix it as per whatever the comments required, and then additional changes were then requested 23 times before their first code changes were actually merged in. Design quality, especially at industry level companies, is incredibly important. We really want to make sure that we're doing a good job so that we're designing code for a feasible future. I'm not sure what else might motivate code, the importance of design quality, if not a story from Google, but here we are, right? So really, I'm hoping that this motivates this week's topic in a way that will engage you. All right. So let's start with talking about this idea of cohesion. So the idea of cohesion is that a class, it's basically what the class does. How cohesive is it within itself? So a high cohesion piece of code, a code that has high cohesion, is a class that does one thing and does one thing well. So here we can see that we have a student class, and the student class stores information. It has getters and setters, and it has a toString. And what's its responsibility is the question we're asking ourselves, right? Does it do just one thing and one thing well? Here we can see a very different example. It's similar in that we're talking about students with names and IDs. Here we have a student report that has a name and an ID listed right here. But now, instead of just being responsible for storing student data, you'll notice now that this is responsible for storing student data and calculating the GPA and generating a report card. That's too many things. We've discussed sort of listening in for the keyword and before, when we talked about sort of designing code and what are some sort of ways to break that cognitive inertia. We don't want code that has low cohesion. We want highly cohesive code. Using the word "and" to describe a class is most often linked to these classes that are sort of not particularly cohesive. The other term that I used at the start of this video after cohesion was coupling. And coupling is the idea of dependency on components. So how dependent are we on other components? When I say we, I mean like a class. So if I'm class A, how dependent am I on class B, class C, class 22-4, whatever, right? We understand. Basically, and you'll notice I'm saying class. I'm not saying primitives. I'm not saying, are we dependent on an integer? Because of course, student ID is going to be an integer, and there's no way around that. But effectively, what we're saying is, how dependent are we on non-primitives? And are we doing it with intention? So this isn't about removing all possible coupling or all possible low cohesion moments. It's about bringing attention to these details and making sure we understand and can defend the reasons why things are set up the way that they are. Because more often than not, you're asked why something's set up a certain way, and your answer is, I don't know, it's just kind of how I wrote it. Whereas we want to have defensible, well-designed choices behind our implementation. So let's start off with, once again, the high version of this concept. So high coupling. Now, previously we had high cohesion being a good thing. Here, let's just notice that high coupling is a bad thing. So let's look at this code. We imagine that we have some kind of a class with a method in it that's responsible for pretending to roll a die and return the value that was it rolled. Okay, so some kind of dice roller class, right? So we understand that we probably need to use a random number generator. All sides are equal chances of getting them anything between 1 and the number of sides, so +1. How do we actually test this code, right? So we talked a little bit about how we would discuss random as stupid cat. How do we actually test this code? We discussed earlier that we would run into these situations and we would discuss it more, and this isn't really going to be a deep discussion into how we would test this code, but we will pay attention to the fact that because this method is dependent on the random object, we're stuck, right? Our random object right now is embedded, hidden away into this method. This method is completely dependent on random, and we have no way to make any changes to it without having to change the code. So even though I want to change my dice probability, right? If I want to change with the tamper with the probabilities, make it a loaded die, even if I want to test the method, right? I want to test roll dice. I don't have a choice right now with the way it's written, but to interact with random, let it be random. And I cannot change the behavior of this method without also changing the behavior of all of the internals here, because all of the internals are directly reliant on things declared internally. They're all locally scoped, right? This object is locally scoped. So really what we're talking about is locally scoped objects creating high coupling. Here we have a low coupling example, right? We can see that random is now being passed in. And when we pass in random, instead of directly instantiating it inside, I can now choose if I want to seed random with a specific value, or if I want to make any sort of initial adjustments to my random object through its constructor before I use it to call .nextInt. So this is better, but we can actually get even better than this, although this will be probably the solution for most of us, which is this idea of rather than instantiating variables inside of methods, instead of locally scoping those variables, we turn them into parameters. We can take this one step further, and we can actually make our own class. So now we're not reliant on the Java-based random class, but rather we can make an interface and then make our own dice class, like a dice interface, and then our own random generator that implements that dice interface. And now we have some real control over what it is that we're trying to do here, right? So here's our dice interface that we would make. Rather than it being another instantiable class, we make it an interface. That's going to make our lives a lot easier for things like testing, if you think back to what we discussed last week. And now I can make a standard random or a loaded random die that are implementing that dice interface. And I have completely decoupled my roll dice function from the die itself, right? Any die should be rollable. They shouldn't be quite so tightly coupled. I have now been able to separate those entirely. And now, rather than roll dice being dependent on the random class or the random class being directly instantiated, both are now dependent on this dice interface. So interfaces are always going to help us with those situations. So here we are making an interface for this one situation, right? But what happens if we're making, I guess because we're doing rolling dice, we have a casino, and now we need a slot interface and a blackjack interface and a poker interface and a bar tab interface, and how many classes or interfaces becomes too much, right? Surely we don't need to do this for every single possibility of situation. And you're right, the answer is that we don't necessarily need to do this for every single situation. But this comes down to one of the key sort of features that come with this class. And when I say class, I mean Comp 3350. And that being that rather than me teaching you a framework or a language, or even like an individual concept, what I'm really giving you or hoping you're going to get out of this class is a toolbox. I am giving you a toolbox of tools, and you're going to choose what tool is best suited for the job. Sometimes you need multiple tools. Sometimes you don't really have a tool for the job and you have to cobble together some kind of makeshift solution. And sometimes 90% of the time now you'll have the right tool in your toolbox, right? So really what this is about is not saying every single time you use the new keyword, you need to make an interface instead. That's not what this is saying. Just because I'm giving you a hammer doesn't mean everything looks like a nail, but it is giving us sort of more to think about when we're designing our methods in our classes, right? It said, surely you don't need this for every possibility. And then I said, you are correct, and don't call me Shirley. If you've seen Airplane, the movie, you will think I'm super funny. Okay, let's hit up our very first of very many acronyms, and this is YAGNI. You ain't gonna need it. If you don't need the interface, you don't need to make it right now. It's easy to add an interface and wrap stuff in it later. We don't want to over-interface everything and over-abstract everything just right from the get-go, right? That overcomplicates very simple code that maybe is fine simple. We just want to be thinking about these things while we're writing our code. For example, if my child came to me and said that they wanted to go to the corner store, building them a rocket ship would be a really bad idea. For example, they cannot fly a rocket ship because they are a child, right? I can't even fly a rocket ship. That would be a really overcomplicated solution to the problem of go and grab your bike, kid, and go get your ice cream from the corner store. So if I don't need to build a rocket ship, I probably shouldn't. If later on my child says, hey, I want to go to space, maybe at that point in time I'll realize a bike's not going to cut it. We're going to have to learn about making rocket ships. So it's not a terrible analogy. So it's the same idea here. Yes, you could make interfaces from the get-go, but you could be making something overcomplicated that you're not ever going to need. And then maybe one day somebody comes to you and says, I actually am going to want to go to space. And you recognize, okay, now I am going to need an interface. And we can go back and with well-structured code, we can refactor it reasonably easily. Here's that exact example, right? We don't build a rocket ship to go to the corner store. So we build it as we need it. We build out what we need, and then when we realize we need something more, we're going to refactor it, and we'll make it different, we'll make it bigger, we'll make it better, whatever that might look like. Now, this doesn't mean never think about your code. Just write code, and then if I need it, something different, I'll refactor later, right? That would be reckless but deliberate technical debt. So I'm not suggesting that you don't think about your code at all, right? I really want to drive home the point that this is not about always making interfaces or only ever making them just in time and not ever making them ahead of time. If you know that in 3 iterations, your plan is to add stuff that will need an interface, you should make an interface. If you don't see anything on your roadmap for the next 2 years, maybe you don't need an interface right this second, right? So we really do want to make sure we're sitting down and thinking about these decisions before we make them, so that when your product manager or your instructor comes to you and says, why did you include this interface, or why didn't you include an interface, you can say, well, we thought about it and these were our reasons. Because that's really what it comes down to, is defendable reasons. All right, the last piece of information that we're going to cover today in terms of these design principles is this idea of separation of concerns. And here we are with another acronym. So it's often abbreviated as SOC for separation of concerns. And this is the idea that we should be splitting up our responsibilities. This is very, very similar to the idea of something being highly cohesive, right? We have logic that should live in logic spaces, and data in data spaces, and UI in UI spaces. When we have like an MVC or layered architecture like we're using right now, these are great examples of separating out our concerns on an architectural level. But we also can separate out concerns lower levels, right? Like we saw an example of low cohesion in code where we had like student data being stored with report generation with calculation details, and those could be easily separated into 3 separate classes and then recombined in like more of a composition style design in your code. Right? So when we think back to what our diagram looks like, we in our project have this data or domain specific object package. That's what DSO is. It's going to be domain specific object. So we have that, or a model package, whatever you've called it. And all it should be doing for this project is representing what things are. This means that all it does is define structure, no behavior at all. In the real world, this might be different. You might have richer data models. But in this course, in this project, we're really focused on anemic models, which means basically just getters and setters. Pardon me, probably mostly just getters. Our data models describe things, right? It describes the nouns, not the verbs. It knows what it is, but not what it does. There is no behavior, there's no business, it is just blueprints. And so that is going to be our separation of concerns in our object class, because very often I'll see logic start to creep into your object class when it really shouldn't be there. Now, the one gray area here is some of you will write your own compare tos and implement the interface comparable, and then you'll have a compare method in your object. That's okay. That's okay. Having a compare makes sense internally. We're going to accept that as part of sort of the base object. Things that we don't typically accept as part of that base object are things like validating the information inside of an object, right? That's different. So we wouldn't do that inside of an object, not within one of these anemic data models. When we think about our persistence package and what it does for thinking of these separation of concerns, well, it saves things to the database and it fetches things, and that's it, right? Repositories, data access objects, ORM mappings, like all of these things talk to the database, not the business. It knows how to store the data, but it doesn't know why it's storing it, right? It fetches facts, not reasons. So our persistence layer should not be doing any kind of validation outside of like normal parsing or whatever that it might do coming from the database potentially. But it really is, its only job is to store stuff. It takes stuff from the business layer. The business says, hey, store this for me. And the persistence layer says, okay, sure. And it should store stuff. And that's all it does. What does our logic and business layer do? So we've done objects, we've done persistence. Now we're on our logic or our business layer. This is where all of those decisions and coordination should happen, right? So we're thinking about it like the application rules, the workflow, the orchestration of this flow. It's really the brain. It's not the hands, it's not the eyes, it's the brain. It's the decision-making brain. The eyes that see stuff or that does stuff, those are other parts of our code. Our eyes might be our UI, right? This is the decision maker. It makes decision, it does not make data. So we should not have seed data being made in our logic layer. We should not have dummy objects being created in our logic layer, right? It does not display. We should not be having view models in our logic layer. We should not have text fields in our logic layer. All it does is help us make decisions. It tells others what to do, but it doesn't do their job for them, right? It doesn't do the display for them. It doesn't create the data for them. Those happen in other places in our code. So this separation of concerns is so important for keeping our code highly cohesive and having a low coupling. Lastly, we have the presentation layer. And what does the presentation layer do? It talks to the user, right? It shows and takes input. It's not in charge of thinking. It's not in charge of storing anything. It should speak human. So that means it should be written in a way that makes sense for humans to see and read and interpret, not database error messages or business logic exceptions, right? It knows how to say things, not what to say. So it gets the information on what to say from the business layer, and then it displays it itself. So hopefully these sort of examples of how each of these layers are meant, like what their concern of each of these layers are, will really help you sort of solidify what parts of your code belongs in which layer. And then of course within each layer you may have additional sub-packages where you also have to ask yourself, what does this sub-package do? Make sure you've got that really nice separation of concerns going on. So like I said, we often find we need further sub-packages in our layers. Within our persistence layer, we might find that we need a separation between your real database and then your stub database, and maybe even more. Within your logic layer, you may find you want to group things by feature or possibly by functionality. It kind of just depends on how you have things set up and what your code looks like. And within your presentation layer, you may find an additional sort of architectural pattern emerges to help organize your code there. Often we find this one is our MVC architecture, and it's also the hardest for us to make decisions on because often people find that the presentation layer is the trickiest to sort of determine what should go where. So I'm hoping I can sort of shed some light on that right now. So here I'm just saying we're going to sort of focus in now on that presentation layer, but that doesn't mean that you can't have sub-packages in the other layers as well. You can, they're just a little bit easier to sort of suss out. So within our presentation layer, we may adopt an additional sort of pattern of packaging. The M in MVC stands for model. So this is going to be the UI model. It is not a domain model. So they are very similar. They hold memory in the same kind of way. They may hold information in a similar way, but it's not a copy-paste scenario here. So this UI model, its job is to hold the screen's memory. It should know what the page knows, not what the entire app knows. So if you're on a specific page, you're on the login page, you're on the leaderboard page, you're on the recipe page, it doesn't need to know about all recipes. It knows about a specific recipe, right? It doesn't know about the global leaderboard if you're on a local leaderboard screen, or it doesn't know about the achievements if you're on a high score leaderboard screen. So we really want to make sure that we're focusing on knowing what the page should know, not the entire app. And it basically will help us remember what the user just saw or just typed. So if the user typed something in and we need to, get it packaged up and stored away, we put it in a model in the front end that we can pass to the back end later to sort of help us with that validation and moving data around. There's no business rules in here. This basically is just the view state. It's just holding state for us. So next we have our view, and what is it that our view does? It does exactly that. It's just a view. It's like looking out your window and you just have a view. It shows stuff nicely. It's the outfit, not the brain. It doesn't make decisions. So imagine we have a view that is the login page, a view that is the you've successfully logged in dialog box, and maybe a view that is the you didn't type in your information correctly dialog box, or something like that, right? That might be pretty redundant, but we can understand that those are just different views. It's not actually in charge of deciding when it should show itself or collecting data. Its only job is to look beautiful. And then it's the outfit, right? It's the outfit, it's not the brain. But then how is it that we connect our models and our views together so that the stuff that comes in through the view gets stored in our model and gets sent to our backend when we're ready? Well, we have our controllers. So the controllers are the ones that are actually going to translate those clicks into calls. It's kind of like the bouncer. You click, go over there. It hands the data off. So it doesn't actually do any of the work itself, but it will hand it off to the back end. So when the user clicks submit on the front end, a listener and the controller will take in all that information thanks to the model, pass it to the back end. The back end should send it all the way to the persistence layer, or it should throw some kind of exception if something went wrong. So we try to make it work properly. The controller can try to do that send. Providing it all works, it can show this login successful screen, or it can catch the exception that the service layer through, and instead it will sort of display the you entered the wrong information screen. It just basically listens, decides what to do, and then it gets out of the way. It doesn't have any view, it doesn't store any data itself, it doesn't do any logic. It's just the remote control that coordinates these different pieces on the front end. So when you have a minute, you're gonna wanna probably go and check out the bonus videos so that you can get an example of what the refactoring might look like for these situations with poor separation of concern. low cohesion instead of high cohesion or high coupling. So I do show some code in my sample, in my example bonus videos where you can sort of see just a little bit of what it might look like when code is written kind of poorly and how we might want to refactor it into just cleaner, more well-balanced, better designed code. Hopefully you watch the refactor video that I just suggested. And then once you've done that, you can go and look at one of the classes that you've written in your project, or perhaps one that somebody else has written in your group, and ask yourself if it's doing too much, because a lot of the times our classes, especially at this point in the course, are doing too much. And they most likely are very tightly tied to something else. It might even be our database. It might be really tightly tied to our database, which could potentially be a problem. If you see these things, make some Git issues and plan to address these design quality concerns in your next meeting, the next time you and your group discuss it. But make sure that you don't just sort of tuck it away in the back of your head. Make some Git issues so that everybody is on the same page and can kind of get a feel for what it is that you're all looking for with respect to, code smells and design considerations. Cool. So hopefully you watched the refactor video, and then after that I will see you in the next video where we will talk about even more acronyms. We have so many acronyms this week as we learn about all these different design patterns and ways to fix kind of stinky looking code. Thanks everybody, and I'll see you in the next video. Bye.